42 joules of work is done to set a metal sphere rolling. And we're going to assume that that is done with 100% efficiency. In other words, all of those 42 joules is converted into the kinetic energy of motion. If the mass of the sphere is 250 grams, how fast is the sphere rolling, assuming no slipping? And that no slipping means it's not slipping over whatever surface it's rolling upon, which, because if it did, right, that would represent, I think, a loss of mechanical energy there, a gain of thermal energy as a result of that. So we've already said we're ignoring that. So I think the concept that we can use for this is that work is equal to a change in energy. This is the broader concept I'd like to start out with. We're talking about a sphere that has been set in motion onto some surface. So it's moving with a velocity v as a result of, again, this amount of work being done to it in some way that was done without any losses due to friction, which actually sounds maybe a little bit hard to do in practice, but that's what we're assuming. We said that there's a translational kinetic energy and rotational kinetic energy, so maybe the way I could break this down is to say there's going to be a delta Ke plus a delta RKe for the rotational kinetic energy. In terms of formulas, that's going to be 1/2 mv squared. This is a change though, right? So maybe this could have been like 1/2 mv squared minus 1/2 mv naught squared. In other words, final kinetic energy minus initial kinetic energy. But I'm going to assume that the way this is worded says is set a metal sphere rolling. I'm assuming that means it started at rest. In other words, I started with this metal sphere sitting there. I did some work to it. Now it's rolling, right? So I think that's fair to say that that means it started at rest and winds up with that total amount of energy, 1/2 mv squared. And the rotational energy it winds up is 1/2 I omega squared. We're being asked for how fast it is rolling, which I think it makes sense. That means we're being asked for speed. Speed is kind of embedded in rotational or angular speed, angular velocity. So we're going to need to do some familiar, hopefully at this point, looking manipulations with this expression here. In other words, since this is a sphere, the moment of inertia is 2/5 m r squared, and then times omega squared. But omega squared together with r squared is going to become a v squared. So at the end of the day, we have, maybe not quite at the end of the day, 1/2 mv squared plus this would simplify to 1/5 m v squared, which, this is why I think I was premature in saying end of the day, because I still need to add these fractions, and I guess mentally I wasn't ready for that. So let me see. I think that is right, because this would be like, you could say 5/10. This would be like 2/10. So I think that's 7/10 m v squared. And all this was still equal to the total amount of work done, right? So let me just put that W here, because the thing that I'm being asked for this whole time, right, is what is that? So if I multiply by 10/7 and divide by mass, I would get that V squared is equal to 10/7 multiplied by that work divided by mass, which if I then square root both sides is going to imply that V is equal to the square root of 10/7 times work over mass. And I've really left it to the bitter end here to plug in numbers. If you wanted to do that earlier, that's potentially okay. I could understand. We have 42 joules. Let's see, divided by 250 grams. I think I'd want to express as 0.2. Let me make that 2 look better. 2.5 kilograms. And a joule per kilogram, it turns out, is a meter squared per second squared. Remembering that a joule is a Newton times a meter, which would really be in kilogram meter squared per second squared. The kilograms cancel. So if I put the numbers into my calculator, I'm going to do the square root of 10/7 times a ratio of 42 to 0.25. And my calculator says 15.4 4919. Boy, that's pretty close there because I'm supposed to round off to 2 sig figs here, but the rounding rules say that would be 15, and the units should be meters per second. So let's check that against the slide, and it looks like we got it.